So hopefully you concluded that the correct answer to that multiple choice question was D, that all of those forms of memory lose their data when you lose electricity. So let's talk about some memory that doesn't lose data if the supply voltage is turned off. And this is referred to as non-volatile memory. Historically, this has been referred to as read-only memory, but this is a bit of a misnomer now because a lot of the newer forms of non-volatile memory can be written to. So let's start with programmable ROM, or PROM. This was a truly read-only memory because it was programmed by blowing fuses. So if the fuse was blown, it was one value, 0 perhaps, and then if it was blown, it was 1. So this was a permanently programmed read-only memory. And then there was erasable PROM, which could be reprogrammed using ultraviolet light. So this was, mostly read-only, although it could be changed using special instruments. And then there is electrically erasable PROM. So this is non-volatile memory that can be reprogrammed using electrical signals, which of course makes it more accessible because you can have devices that are available to consumers that can change the memory values. And this is the basis for flash memory. So the USB thumb drives that you're familiar with, this is the technology that these devices use. So these devices don't need a constant current in order to preserve their value, but they can still be modified using just electrical signals. There are also some non-volatile forms of SRAM. So there is battery-backed SRAM that maintains power, or maintains its value when the power is off by virtue of an external battery. There's also a newer technology called non-volatile SRAM, or NV-SRAM, and this handles reads and writes the same way as SRAM, but there is a non-volatile component for permanent storage. And there's a capacitor that provides energy if the main current is lost. Okay, so let's talk about disk storage systems. So these are forms of non-volatile memory that are used to store large amounts of data. And it does so using technologies that are slower, but are far more cost-effective than either SRAM or DRAM. And so we can usually build much larger banks of these kinds of storage systems. So the one that you probably have in your computer these days is something called a solid-state drive, and these are basically just flash memory organized into blocks. And this is what is sort of used for a lot of the mass storage in modern devices. A slightly older technology that you may still have in your computer, especially if it's not a laptop, is something called a magnetic hard disk drive. These were fairly common a few years ago until solid-state drives became economically viable. So these, the magnetic hard drives actually have physical platters that data are written onto, and they have the surface that's coated with a magnetic material so that the data can be stored. The data is accessed using a physical arm, an actual physical device inside of the drive that rotates and has a head that is used to read the platters. So the data is stored on tracks that go around these cylinders, and the tracks are partitioned into sectors. The capacity of these hard disk drives is based on the area of the disk. And so it's kind of a product of, how dense can you record data on the tracks, and then how densely can you pack the tracks onto the disk. And the important thing to acknowledge here is that the operation of these devices requires mechanical motion. You have to wait for an actual device to move inside of the hard drive. And this thing that moves is called the actuator arm, and it has the magnetic read-write head on it. So the speed is going to be based on the access time, how long it takes for this magnetic head to get to the data that needs to be read and to read it. And this is going to be the sum of the seek time to move, the rotational latency for the disk to spin around, and then the transfer time to get the data out of the device. And the platters spin at a standard rate in one direction. And so if you didn't catch it during the spin, you have to wait for it to come around again on the next spin. And so there's this disk controller, which is the part of the device that actually coordinates access to the data, and it performs this mapping of logical blocks down to actual locations on the disk. So if you're looking at this from the perspective of the CPU doesn't have to be aware of the low-level details of where things are stored. Okay, so given that knowledge, it's worth pausing for a second to think about what data access pattern will give the highest performance with one of these magnetic hard drives. Sequential, so just bytes in sequence, every other byte, reverse sequential, or random, or it doesn't matter, they're all the same. So take a minute and see if you can identify which of these is going to be the slowest, or the highest performance, actually. So as we said, data is read off of this device as the device is spinning. So the data that is laid out right next to each other on a track, you're going to be able to read all of those in sequence more quickly than having to jump around to various tracks on the disk. So the answer here is A. Sequential access is going to give you the highest performance with a magnetic hard drive. Okay, so there are also some even less expensive and larger storage options, memory technologies. So we often refer to these as archival storage systems because they are often used to store archives. And this is because they are quite slow to access. You wouldn't want to do daily work from a device like this. But these these always come with the lowest cost per byte. And so if you need to store a lot of data for a long term, these technologies are going to be good options. So believe it or not, we still use tape in a lot of places for storing long-term archival data. So this just stores data on a magnetic tape like a cassette tape or a VHS. These are often in an off-site location for added redundancy. There are also a variety of network-attached storage systems. These are basically using someone else's storage. So these are dedicated data storage servers that often use redundant disks for reliability using a technology called RAID. You would communicate with these over a network via some sort of file sharing protocol. So sometimes these would be in-house, but frequently they're managed by a third party. And there are a variety of technologies that you would use to access these things. We won't talk much about this in this course, but you will revisit these things if you take, in particular, 470, which talks about parallel and distributed file systems.